All right, hello, welcome to Mr. B's Biology. This is a lecture on partial pressures of gases. I teach anatomy and physiology among other types of biology classes, and inevitably when I teach anatomy and physiology, I have students that are a little bit confused about how this whole partial pressure of gases works, why is it relevant, especially in terms of gas exchange between the lungs and the pulmonary capillaries and between the systemic capillaries and the interstitium. So I'm going to kind of touch up on that today. So obviously, if we're talking about gas exchange, we first have to talk about air, because air is what we're breathing in. And what is air? So typical air consists of different types of gas molecules at these different concentrations, but ultimately what we see is we have N2, diatomic nitrogen, O2, diatomic oxygen. Of course, I'm sure you all know carbon dioxide by now, CO2, and of course, H2O, water. And there's other things such as argon, neon, etc. So there's other types of gases, but we're just going to focus on these, particularly obviously oxygen and carbon dioxide, because that's relevant. But if we just focus on these four gases, they essentially together constitute this number right here. So we have 1 atm at sea level, and this obviously can be within a range. It doesn't mean you have to be right at sea level to see 1 atmospheric pressure or 1 atm. But the other way we can represent this by 760 millimeters of mercury. All right, so if we look at this number here, 760 millimeters of mercury, regarding these gases, these four gases, nitrogen usually is about, let's say, about 78%. Oxygen usually is somewhere around 21%. And then carbon dioxide and water together, they're going to be about 1%. A little bit less than 1% actually together. All right. So if we take this number, 760 millimeters of mercury, this is going to equal the total pressure of gases in air. All right. So that each of these molecules are going to be a fraction, a representative fraction of this 760 millimeters of mercury. So 78%, 21% for oxygen, and of course less than 1% for carbon dioxide and water together. So if you added all these numbers together, you basically would get the 760 millimeters of mercury. So they're typically represented as partial pressures. So often they're denoted as a P, or sometimes you might actually see it as a big P with a little a for partial. All right, I'm going to stick with the little p here for now because I just think that'll be easier than trying to write it all out. All right, so if we take 1 atmosphere, 760 millimeters of mercury, it would essentially equal the partial pressure of N2 plus diatomic oxygen, O2, plus partial pressure of CO2 plus partial pressure of H2O. All right. And again, these are fractions. These are percentages of that total number. We're only going to focus particularly on oxygen and carbon dioxide. So oxygen, you would get about 159 millimeters of mercury. And for carbon dioxide, you would get somewhere around about 40 millimeters of mercury. Okay, and of course you add the other numbers with nitrogen, diatomic nitrogen, and water, and some of the other trace gases, we get 760 millimeters of mercury at or close to sea level. All right, so let's look at these numbers when it comes to looking at comparing, the air within the alveolar space. We just breathe in. It's worked its way all the way through those divisions of the respiratory system. We get down to the smallest division here, the functional unit of gas exchange, which is the alveoli. And within the alveoli, we'll see that obviously we have these partial pressures of these gases because of the air that we breathe in. And we're actually going to see that within the alveoli, it's going to be partial pressure of oxygen, we'll just keep it there. All right, partial pressure of oxygen is actually going to be about 104 millimeters of mercury. And the partial pressure of CO2 is going to be about 40. All right, so automatically, I imagine most, if not all of you, have hopefully picked up on the fact that you said, wait a second, 159 millimeters of mercury, that is the fractional representation of oxygen in that total amount, that 760 millimeters of mercury. You are right. So 159 in the air, but only 104 typically on average within the actual alveolar air of the alveoli. And that's because, particularly with the humidifying of the air as it's passing through the respiratory divisions, the upper respiratory obviously is a big part of conditioning the air. It's working its way down to the alveoli. That's going to change the partial pressure. So we're actually going to lose some of that partial pressure. We're going to go down from, let's say, about 159 millimeters of mercury to about 104. All right. Lung capillaries, the blood circulating through the lung capillaries, we're going to see a partial pressure of about 40 millimeters of mercury. And, sorry, it should be oxygen. And then partial pressure of carbon dioxide is going to be about 45 millimeters of mercury. All right, so automatically you should see there's some discrepancies in these values, in these numbers, between the blood coming through the lungs, through the lung capillaries, and the partial pressures of gases in the alveoli, because there are some differences here. Why are these differences relevant? So gases, like many things, want to go from high concentration to low concentration. All right. So I'm just going to represent concentration by that little shorthand there. Okay, so gases want to go from high concentration to low concentration. So having higher partial pressures of gases from one area compared to another is going to dictate the movement of those gases from that one area to the other. So for example, 104 millimeters of mercury, partial pressure of oxygen is higher in the alveoli. So therefore, we're going to expect that the partial pressure of, because there's a higher partial pressure of oxygen, the movement of the oxygen is going to go from the alveoli across the respiratory epithelium, the alveolar epithelium, and work its way into the blood of the pulmonary capillaries. All right, so that's going to facilitate the movement of oxygen from the alveoli into blood because there is a higher partial pressure of oxygen in the alveolar space, and there's a lower partial pressure of oxygen in blood. All right, so if we compare that with the other number here, which is the partial pressure of carbon dioxide, compared to that of blood, we can see that partial pressure of carbon dioxide is actually higher in the blood of the pulmonary capillaries, in comparison to the partial pressure of carbon dioxide in the alveolar space, in the air, which is lower. So again, we want to go from high concentration to low concentrations. So that's going to facilitate the movement of carbon dioxide from the blood to the alveoli. All right, so now let's look at it in terms of the systemic circuit and the interstitium, the body tissues. We're going to see, I've already got the values written here, but systemic capillaries, it's 95 millimeters of mercury for partial pressure of oxygen, and the partial pressure of carbon dioxide is 40 millimeters of mercury. Now, again, hopefully if you're astute students, you're automatically picking up on the fact that, oh, wait a second, why is it 95 millimeters of mercury when it was just 104 when we were talking about going from the alveoli to the blood? Why do we keep losing partial pressures of these oxygen molecules? There's a couple situations, particularly as it's traveling through the systemic circuit and the heart, but we have things like shunt flow, so some of the blood is actually bypassing the exchange surfaces between the alveoli and the blood, and they also get some venous admixture of blood as well. So we lose a little bit more partial pressure of oxygen between the alveoli and the pulmonary capillary. So we've lost a little bit again. We've lost a substantial amount, 159 down to 104 because of the conditioning of the air as it's passing through the respiratory system. And then we lose a little bit more because of phenomena like shunt flow. So we go down to 95 millimeters of mercury, between 95 and 100 millimeters of mercury. So it's not a big substantial difference. All right, so we do see some differences in these partial pressures of oxygen and some discrepancies because of different types of physiological phenomena that occur. All right, partial pressure of carbon dioxide in the systemic capillaries is 40 millimeters of mercury. So we compare that to the interstitium that's bathing these body tissues, these cells of these body tissues. We see partial pressure of oxygen is about 40 millimeters of mercury, and partial pressure of carbon dioxide is a little bit higher. It's 45 millimeters of mercury. All right, which should make sense, obviously, because we're generating carbon dioxide through cellular respiration. So we're going to see a little bit higher numbers there. Okay. Partial pressure, I'm going to focus on that one first. Partial pressure of carbon dioxide is lower in systemic capillaries, but it's actually higher in the interstitium because we are generating carbon dioxide as a byproduct. So again, it favors going from high to low. Always remember that. We go from high to low in terms of pressure or partial pressures. So we're going to see movement of carbon dioxide from the interstitial fluid, from these body tissues into the systemic capillary. Partial pressure of oxygen is 95 millimeters of mercury in the blood. In the systemic capillaries, it's 40 in the interstitium. So obviously that's going to facilitate movement of oxygen from the interstitium, from the systemic capillaries, where it's higher, to the interstitium, where it's actually lower. All right, so again, we want to go from high concentrations of these partial pressures of gases to low concentrations, and that's going to facilitate the movement of these gases, whether we're talking about between the alveoli and the pulmonary capillaries, or we're talking about between the systemic capillaries and the interstitium. Okay, so just kind of recap what we just talked about here. I've got my fabulous drawing. I know it's awesome. So at the top here, we have my alveolus. Just a typical alveolus. Partial pressure of oxygen, 104 millimeters of mercury. Partial pressure of carbon dioxide is about 40 millimeters of mercury, what we've been talking about. This little line right here is kind of dividing the pulmonary circuit from the systemic circuit. So with the pulmonary circuit, we would obviously expect, we can see via the systemic veins, bringing that back. And then we get to the heart, right side of the heart, pulmonary trunk, pulmonary arteries, going down to the pulmonary capillaries. We're going to see these similar values here. So we're going to have partial pressure oxygen of 40 millimeters of mercury, partial pressure of carbon dioxide, 45 millimeters of mercury, as that blood's traveling through that pulmonary circuit, getting ready to do some gas exchange between the blood and the alveoli. All right, so because of that, we would expect that we would see a movement of oxygen from the alveoli, where it's higher, to the blood and the pulmonary capillaries, and obviously the movement of carbon dioxide where it's higher to the alveoli, to the space within the alveoli. All right, now we've just oxygenated, we picked up oxygen via the pulmonary circuit. Now we're going to travel through the systemic circuit via the systemic arteries, and now we have 95 millimeters of mercury. Partial pressure of oxygen, partial pressure of carbon dioxide is low, 40 millimeters of mercury, compared to the body tissues, which also have these same values here. Partial pressure of oxygen is 40 millimeters of mercury. Partial pressure of carbon dioxide is 45 millimeters of mercury. So again, because partial pressure of oxygen is higher in the systemic capillaries than in the body tissues within the interstitium, that's going to facilitate the movement of oxygen from the blood, in this case, to the interstitium, towards those body cells. All right, because we generated carbon dioxide as a byproduct, it's higher in the interstitium from these body cells, from these body tissues. That's going to facilitate the movement of carbon dioxide from those areas back into the systemic blood. Okay,